Thanks. Yeah, hi, I'm Marcel. I'm going to talk a bit about this project where we looked at the special case of cloud-based visual localization. And just to give some background, there's actually a short history of collaborations between our group at ETH and Microsoft looking into this, particularly privacy for this visual localization in a cloud-based context, because that's where you want to preserve privacy. And the line of research is especially interesting for us, for this project here. It's basically started with two projects done by Pablo Speciale back in 2019. So in the first project, they basically replaced the point cloud as used as a map for localization with a line cloud by simply passing a randomly oriented line through each point. And then they showed that you can still localize an image just from image key points against this line cloud. Second project, they basically applied the same idea to the image key points. So instead of using key points in the image, they replaced those with the 2D line, and then again you can localize this, in this case against the point cloud map. And then later, we basically extended this second version from just a visual localization system to a full structure for motion pipeline, which is especially relevant if you want to update your map to reflect changes in the environment. And the reason why we are going through this is basically what we had just discussed in the last questions. Turns out there was this work in 2019 as well by Francesco Pitaluga, not from our group, but actually, again, a collaboration with Microsoft. And there he showed that from just a point cloud with associated SIF descriptors in this case, you can reconstruct the images, or actually even new images with the virtual camera pretty nicely. Just in this example, we're using the image key points directly. So here on the left, you see the original image. In the center, it's just the key points visualized. And if you combine this with the corresponding SIF descriptors, pass it through a network, you can actually get an image like on the left. So that probably solves Mihai's problem for the proper latent space. But in the current project, we basically try to look at a different problem. Because if you look at cloud-based localization from a client point of view, like you have this mysterious cloud as a black box, you just send an image and it gives you back a pose, which is pretty nice. But if you look at what is actually happening in there, obviously we have a map of the environment. And the more often we localize in there, the cloud can basically just log the poses, get trajectories, not only from a single user, but maybe from more users. And there's works that show that especially for the larger scale data sets, so these are usually not from visual localization, but let's say from Google Maps, GPS data, even if it's anonymized, you can get a lot of data out of this, basically figuring out who this person is by just looking at home address, work address. You could find habits by just looking where people are going, probably doctor's visits, all of this stuff. And that is like really sensible information or sensitive information that is probably more obvious compared to just looking at the poses where we've been. So just to give a very brief overview of what you're doing, we're again applying the same idea as in the previous works. So we are adding degrees of freedom to our geometry. So we start from our private map here in the bottom left. We split the map actually into 3 parts. And for each one, we choose a separate direction that we want to use for localization. And then we actually create planes instead of the lines before. And the important part here is that we're using parallel planes instead of randomly oriented. We can distribute these maps to different servers. And then at query time, we basically just send a point cloud to each server separately. and we get a partial pose back, and we can fuse this locally to get our full pose again. So this is probably a bit abstract, so let's look at an example here, or some visualization. So that we start from a camera pose plus structure. So we have actually a local point cloud with descriptors. And this is actually the case that has been shown in the earlier works to be already kind of a privacy violation. So we are leaking the scene appearance here, but we explicitly decided to ignore this problem for now. We are really focusing on like hiding the pose. And we're using this, we can basically just find correspondences to our plane map. So this is one map, parallel planes, align it there. And what happens if you have these constraints, so just trying to put each point in the corresponding plane, is that we can move the camera around a little bit. We can move it in both directions parallel, orthogonal to the plane normal, and we can also rotate around this plane normal. So just looking at the position, basically the camera position is constrained onto a plane in 3D. Now, this is not super helpful in most cases, but what we can obviously do is we use multiple of these plane maps with different orientations, and then suddenly we get multiple constraining planes, and this is already more helpful. So we can just fuse this, and from two maps, we basically constrained our pose that we only have a single degree of freedom on the position. So in this example, it's like up and down, but it depends on which plane normals you choose. What is also important to notice that from those two queries, we can already fully constrain the orientation. So we usually have one rotational degree of freedom per query. If we combine this, the orientation is already fixed. But obviously, if we want to know our exact 6 degree of freedom pose, we can just do the same trick again. We have a third query with, again, a different normal direction. We add the constraint, and then we get the full pose. So just quickly looking at the overview again, you can see I'm basically showing here only two queries. And that's the nice thing about this method as well, because in many cases, we might actually not need the full 6 degree freedom pose. We just want to have some 2D localization in map, let's say for autonomous driving. And there it's actually sufficient to just use two maps, two servers. So this already increases our potential to leak some data somewhere, like smaller attack surface and all of this. Now just to quickly show how we do this, we basically start from a constraint to align 3D points. So let's say we have a query point as xq and a map point xm. We're just trying to find the rotational translation that those get to the same position. And in a bit more detail, it's basically just we're rotating the query point, adding a translation to get to the map position. And if we look at this a bit more closely, we can see that there's probably a highlight missing here. Do I have? Yes. So basically, we can use this first row of the rotation matrix, multiply it with a point, add one translation, and we get this x here. So we can extract the constraint for like a single dimension out of this whole thing. And obviously, it's not just for x. We can do this for all of them. Unfortunately, you cannot really see the highlights here. But basically, yes, for one direction, we take the first row of the matrix, first element here, second row, second element, and so on. And there we have like the constraint around the three main dimensions. So just quickly show how we actually get the pose. I promise this is the most math slide in the set. It's really just a small rearrangement. We have the query points on the left-hand side. We have the plane offsets along the normal direction on the right-hand side. So it's important we can actually use the exact same formulation for all 3 dimensions. We're really just storing the point offset along the chosen map normal direction for each map. And then we can solve for this vector, which is basically the row of the rotation matrix plus this one translation component. And we are enforcing the norm of the rotation matrix so to be 1, just because rotation matrix has to be orthonormal. What we cannot do here is to basically enforce actually orthogonal rotation matrix rows, because we're doing every query independently. But it turns out if we have sufficiently good correspondences, we're actually getting really close to a proper rotation. So when we are later fusing the pose, we're basically just projecting back to the rotation manifold, but it's already very close. Yes, so for map creation, we need to be a bit careful, because obviously if we just replicate the original point cloud 3 times and then create planes in 3 different directions, if anyone obtains those 3 maps, you can just intersect all of it, you get the original points back, and we don't want that. So what we do instead is, as I mentioned before, we basically split the map or the point cloud into 3 separate parts. They're all disjoint. And then for each one, we choose a plane normal direction, create the planes, and then we can throw away the points. To just give some quick results here. So as I said, we require some structure. So for these experiments, we used a large-scale SFM data set, and we just triangulated points from a few images around the query. We compared this basically with 2 other methods. First, it's a standard point-to-point alignment, so we have point cloud directly to point cloud. The second one is actually a variation of the random line clouds by Pablo Speciale. So there they, again, create a plane map, but randomly oriented planes. And you can query this as well with a query point cloud. And then we have ours with the separate queries. And again, we're missing highlights here, which is a bit unfortunate. Basically, what is important, is the third row here. So we have a slightly larger error threshold. It's like all poses, or the percentage of poses within half a meter or in 10-degree offset to the ground truth. And obviously, the point-to-point alignment is the most robust one, just because we get the most constraints out of it. But compared to the point-to-plane, basically the splitting of the queries doesn't have a huge impact anymore, so we are kind of close to this. And in return, we get these additional privacy benefits. Then also we can obviously just get structure from active depth. So this is the 7 scenes data set with a Kinect. So you get depth directly. Also the scene size is much smaller. So this is an indoor data set. Before it was a large-scale SFM. And what we can see here is there's this one scene, this, stairs, the yellow one, that has just very bad correspondences. And you can see the other 2 methods are also suffering a bit from that, but for the split queries is actually much worse. On the one hand, it's because the point-to-point alignment needs 3 inlier correspondences to find a good pose. Point to random plane requires 6, and for the split queries, we actually need 3 inlier correspondences for each query, so 9 in total, and they also need to be distributed correctly. But what is really nice for the scenes where we actually get good correspondences, we are staying pretty close to what the other methods can do as well. And I think this small decrease in accuracy is probably okay if we get the additional privacy benefits. That's already basically what I wanted to tell. So thank you for listening.
Okay, do we have any questions? Right, so maybe I can ask. So this is a relatively young field, like, I don't know, 3 years, 4 years maybe, but series of papers haven't. What do you think is preventing, to actually deploy these methods to the real technology? Because what we mostly see is still, point-to-point solvers and other things.
So for let's say the previous works, they are probably a bit closer to practice. For this one here, I have to admit it's mostly like academic interest, because the journal is like for, like if you get enough queries, you can say you could accumulate just the query point clouds, and if you match them to the same planes on the server side, you basically could assemble the point cloud just from the queries again. So there's some danger to like still violate privacy here. And get everything eventually. And then, like, it depends on the application, obviously. For AR, let's say, you really want to have very good poses. There you want to figure out if the poses or the decrease from this method is actually already too bad. You obviously need 3 separate servers, so we need the assumption that they don't communicate, they don't collaborate somehow to get data from the user. And I mean, in general, it's not like everyone is using cloud-based visual localization on an everyday basis. So probably we can deploy the standard version first, and then we try to make it better.
Okay, thank you. Any other questions? Okay, if not, let's thank the speaker.